Hi, welcome to season 2 of QuBites, your bite-sized pieces of quantum computing. My name is Rene from Valorem Reply, and today we're going to talk about quantum computing hardware landscape. And I'm very honored to have a special expert guest today, my fellow Microsoft Regional Director and MVP, Cyprian Djikic. Hi, Cyprian, welcome to the show. I know you as an RD and also that you have your own quantum computing podcast, but can you tell everyone a little bit about it and yourself and your background as it relates to quantum computing?
Hi, Rene. Very happy to be on your podcast. As you mentioned, I'm a Microsoft Regional Director. I'm a most valuable professional on artificial intelligence and quantum computing. You mentioned I have my own podcast. Entangledthings.com is a podcast that I've launched this year. My interest in quantum computing goes way back in college when I was a big fan of quantum physics. I would call myself a failed physicist, actually. I ended up in computer science, but that was kind of my first scientific love, and now I get to practice it with quantum computing.
Nice. That's awesome. And we're not just both regional directors and MVP. We also were both born behind the Iron Curtain and are now working on this modern technology. And that's just awesome. But let's dive into today's topics about the quantum computing hardware landscape. What kind of different quantum computers are out there, and which is, in your opinion, the most promising approach that is being tackled?
Well, I think at the moment, there are two major categories of quantum computers when we speak about the hardware itself. We have the circuit-based quantum computers, and then we have the hardware that is based on quantum annealing. And the big difference between the two of them is that the circuit-based computers are the ones that aim to implement what we call universal quantum computing, meaning that you could run virtually any program on them, while the annealing ones are limited to a specific class of problems that they can solve, namely optimization problems. Obviously, from my point of view, the most promising one is the first, the circuit-based quantum computers, because those are the ones that promise the full power of quantum computing.
Totally get it there. It makes most sense. They're general, right? And with quantum annealing and the optimization you mentioned, you can implement this quantum tunneling approach, right? Where you can just basically skip an energy level, basically, kind of. And so, but that's the current basically approach that we see from some vendors, right? Because it's easier to implement than the circuit-based one, right? And so, speaking of the vendors and the players in the field, if you will. What are some of the major research institutes and also, technology players that are developing their own quantum computers?
Yeah. Before that, I would like to add one more thing, because it's the source of a lot of questions that I get. It's in the number of qubits that are available, right? With quantum annealing computers, you typically see larger number of qubits, but those are not those qubits that are based on the circuit approach, which are basically the ones that we're looking for to get into what we call quantum supremacy. The most important player in terms of quantum annealing computers is D-Wave, and it's the one that actually is driving the field. On the circuit-based part, we have a larger field of players ranging from startups like Rigetti or big players like IBM, Google, and also Microsoft, which has not yet a working physical quantum computer, but it's developing it on a different approach that is based on topological quantum computing. There are also several major universities of the world that are playing in this particular field. So it's a field with some very large players, but also with some very important startups like Rigetti or D-Wave or the others.
And IonQ and a few more, right, that are working in that field. Speaking of the topological qubit approach that Microsoft is approaching, I keep on hearing like that is probably, if they can make that happen, that's probably like the biggest kind of milestone. What is your What are you thinking about that?
Well, the big problem with circuit-based quantum computers is what we call the decoherence problem. And without getting into the math, it's literally the problem of isolating the qubits from the outside world. That's one of the largest problems, the biggest problems these folk need to solve.
Yeah.
And that's the reason why we don't have too many working circuit-based qubits at the moment. Mm-hmm. And this is where Microsoft tries to play differently, in a sense that the topological approach has the promise of making it simpler to isolate qubits, which in turn means you need less physical qubits to build the logical ones, less error control, and obviously you get a more stable system with a larger number of qubits. That's the promise, right? It's a long way to go, though.
Yeah, totally. You already mentioned quantum supremacy, and that some players in the field already announced that they reached quantum supremacy. Maybe you can just tell us a little bit what is actually quantum supremacy, and also what do you think about this claim that was actually made, and then some other players or other companies said, well, that's actually not a real claim. So what do you think about that?
Well, quantum supremacy actually refers to the fact that a quantum computer can execute an algorithm in a short amount of time compared to the time a classical computer would need it. And usually it's several orders of magnitude. Like a quantum computer will do, let's say, a factorization in the order of hundreds of seconds, while a classical computer, no matter how powerful, would need hundreds of years to do it. It actually has two aspects. One is the actual building of the hardware, and the other one is the algorithms that are capable of using it. Unfortunately, from my point of view, this went into the realm of marketing hype. The reality is that today we simply do not have a large enough number of stable qubits. That's the big difference. That's where it's kind of, you know, the fine print. You always need to think about it. It's not about the number of qubits you can build. It's the number of qubits that can simultaneously be in a coherent state so that you can run computing. And at least based on public evidence, we're not there yet. So I have serious doubts that any company today can claim of actually reaching quantum supremacy.
All right, that's good to know, right? It's like saying, hey, we have 2,000 qubits, and then in the fine print it says, hey, but they collapse in a few nanoseconds.
Exactly, right? And we can keep like 10 at a time in a coherent state so that we can run actual computations. And that was a great thing that you mentioned about nanoseconds, right? When we're saying keep stable, you need to think at a completely different level, right? Like, for example, keeping them stable for 2 milliseconds would be an amazing feature of engineering and would actually allow the run of a lot of powerful algorithms. So the time here, the time spans are totally different from what the ones that we are used to work with in classical computing.
Totally makes sense. Well, we're already at the end of our short show today, and thank you so much, Cyprian, for joining us and sharing all your insights about the quantum computing hardware landscape. It's very much appreciated. Thank you so much.
Thank you very much, Rene, for the invitation. It has been a joy to discuss with you this topic.
Thank you. And folks, make sure to also subscribe to his podcast called Entangled Things. It's awesome. And it's a little bit longer than our show here, so you get more details if you're interested in that. So check that out as well. And thanks everyone for joining us for another episode of QuBites, your bite-sized pieces of quantum computing. Watch our blog, follow our social media channels to hear all about the next episodes that we will be releasing. Take care, be safe, and see you soon. Bye-bye.